Hello, friends. Uh, Today I'm going to discuss the thermodynamic portion, which was asked in the IIT JAM Physics 2021. Uh, so the first question that I have with me is, a system undergoes a thermodynamic transformation from state S1 to state S2 via two different paths 1 and 2. The heat absorbed and work done along path 1 are 50 joule and 30 joule respectively. If the heat absorbed along path 2 is this 30 joule, the work done along path 2 is. So basically, here we can see we have been given 2 points, two states, S1 and S2. The initial state was S1 and the system went to the S2, the final state. But two different paths, let's say 1 and 2. And in the path 1, the heat absorbed was 50 joule and the work done was 30 joule. However, in the path 2, the heat absorbed was 30 joule and the work done we had to calculate. So we know that the internal energy is the state function. So when we go from one point to another point in the uh, thermodynamic process, uh, the change in the internal energy will remain same between two positions. So if I apply the first law of thermodynamics in along the first path, you see, so delta Q is equal to delta U plus delta W. In the first path, I have written a delta Q1 equal to delta U1 plus delta W1, and from that I calculate delta U1 as delta Q1 minus delta uh, W1. Similarly, for second path, it will be delta U2 equal to delta Q2 minus W delta delta W2. And since both are changed in the internal energy between the point 1 and 2, and the internal energy basically is the state function, right? It depends only on the position, initial and final position. So I substituted the values given in the question. The delta Q1 was given as 50 joule, and the delta W1 as 30 joule, and delta Q2 was given as 30 joule, and delta W2 was asked the work done in the second path, which comes out to be 10 joule. So option first was correct in the exam that was asked. And this second question, which I have, is the RMS velocity of the molecules of oxygen is given by V at some temperature T. The molecules of another gas have the same RMS velocity at temperature T by 16 instead of T. The second gas was asked. So VRMS is given by the under root 3 RT by M, where R is the gas constant, T is the temperature, M is the molecular mass of the gas. So in case of oxygen, that molecular mass is let me write as M sub O, which is 32. And this is given in the question that at temperature T, oxygen RMS velocity of the molecules of oxygen is V equal to under root 3 RT by MO. And for another gas, let me write this VRMS velocity as VRMS superscript A, the A for another gas, and it has the same velocity as the oxygen has VRMS, but at different temperature, T by 16. So I substituted T by 16 in place of T over here, and the mass of the another molecule of the another gas, which is Ma, I've denoted. So both are VV, so I equated them, and you see that it gives me Mo is actually equal to 16 times Ma. The Ma is Mo by 16, and Mo is 32. So I get Ma, the mass of the molecule of the another gas, as 2, which clearly indicates that the other gas is nothing but the hydrogen, because hydrogen has the molecular mass as 2. So option 2 was correct in this question. When come to the section B of the exam, so the question was asked like an isolated ideal gas is kept at a pressure P1 and volume V1. Okay, so it was an ideal gas, isolated ideal gas. It was kept at a pressure P1 and volume. The gas undergoes free expansion and it attains pressure P2 and volume V2. Identify the correct statements where gamma is Cp by Cv. Okay, so in the case of free expansion, work done is 0, and it's an adiabatic expansion, right? Because in free expansion, there is no pressure to work against. That's why the work done is 0, and there is no it's an isolated ideal gas, so no heat exchange takes place. Delta Q is 0. So in a sense, it's an adiabatic process. So third option is certainly correct. And since uh, it is allowed to expand uh, freely, and the no work is done in this process, in the if you are aware with the free expansion case, then it means it is not spending its internal energy in doing some work because the work done is zero. So essentially its temperature doesn't change, right? So it's an essentially isothermal process through expansion. So if it's an isothermal process, if you apply the ideal gas equation, P1 V1 upon T1 is equal to P2 V2 upon T2, and T1, since it is isothermal, this T1 is equal to T2, so they cancel out and we are left with P1 V1 is equal to P2 V2. So option 1 is also correct. Option 2 is not correct. It's not isobaric because you see the pressure is changing. And her fourth option will also not be correct in a sense, because although it's an adiabatic process, but it's a free expansion. Okay, it's for an usual adiabatic process. The fourth would have been the correct answer, but it's adiabatic as well as isothermal. So this particular equation is not applicable in this particular case. So the options 1 and 3 are correct. A Carnot engine, this is the next question. A Carnot engine operates between uh, uh, TL, 100 Kelvin, basically is the temperature of the sink, and TH is the temperature of the hot bath or the source, 150 Kelvin. Each cycle of the engine lasts for zero point 0.5 second. It takes zero point 0.5 second to complete a cycle, during which the power delivered is 15 joule per second. It means per second 15 joule amount of work is being done. Uh, uh, okay, so let QH be the corresponding heat absorbed by the engine and QL be the lost heat. Identify the correct statements. So it's MSQ, multiple uh, correct answers could be there. So these are the different options given. QH by QL less than equal to 2 by 3, and the change in the entropy of the engine and the hot path in a cycle is 5 joule per Kelvin. The change in entropy of the engine is zero point 0.5 second is 0, and the fourth one is. So according to me, third and fourth are the correct answer. The reason is because if I make a Carnot engine, this is the Carnot engine, right? So TH is the 150 Kelvin given, TL is 100 Kelvin given. So QH amount of is being taken from the hot bath, and some amount of work is being done, let's say delta W from that, and QL is being rejected to the sink. So QH minus QL will be delta W, and we know in case of Carnot engine that this formula we derived in our textbook, and in its study of thermodynamics, that the Q2 by Q1 was T2 by T1, or here in these notations, QL by QH is equal to TL by TH. So if I substitute the value for TL and TH, I got 2 by 3, but that's for QL by QH. In the options, it was given like QH by QL. So this is not the correct option, right? Second thing is, if I substituted the value of QL from this, for example, QL is equal to 2 by 3 times QH. If I substituted it back into the 1, so I get that QH is actually equal to 3 times of delta W, and delta W is nothing but 500 joule per second, and one cycle takes zero point 0.5 seconds. So total amount of work in one cycle is 1500 times zero point 0.5. Okay, because work done, power is basically work done upon time. So work done is power into time. So power is given 500 and times taken is zero point 0.5. So this gives me the work done, and I put the value in the right hand side of equation for the work done, 500 into zero point 0.5, and QL and QH have a relation, which I substituted the value of QL from that relation, and I got QH to be 750 joule, right? And from that I can get QL is nothing but 500 joule. So if I see the option 4 here, it is given that the QH is 750 joules. So this is correct. Okay, now the second and third options are with the change in entropy. Okay, we have to calculate the change in entropy of the engine. So for Carnot engine, if we calculate the change in entropy for engine as a whole, it turns out to be 0. So if I see here, for example, the change in entropy, so you see the QH amount of heat is being liberated from the hot bath at a temperature 150. So total change in entropy will be minus QH over 150, and similarly the same amount of heat, I mean the QL amount of heat being absorbed by the sink at the temperature 100 Kelvin. So if I calculate this, comes out to be the summation of the two comes out to be 0. So the change in entropy for the engine should be 0. Uh, okay, so the third option seems to be correct, third and fourth. Okay, so let's go to the next question. A gaseous system enclosed in an adiabatic container Okay, is in equilibrium at pressure P1 and V1. Work is done on the system in a quasi-static manner, due to which the pressure and volume changes to P2 and V2 respectively in the final equilibrium state. At every instant, the pressure and the volume obey the PV to the power gamma equals to constant, where gamma is equal to sigma by CV. If the work done is zero, then identify the correct statement. These are the options given. And if I see the work done in the adiabatic process is 1 over gamma minus 1 P1 V1 minus P2 V2. If the work done is 0, then we'll get P1 V1 is nothing but P2 V2. So option 4 is correct. Although it was asked in multiple correct questions, so even then, the only one options were correct according to me. Now, section C, consider N1 number of ideal gas particles enclosed in a volume V1. If the volume is changed to V2 and the number of particles is reduced by half, the mean free path becomes 4 times of the initial value. The ratio of V1 by V2 has to be calculated. Okay, so let's consider, for example, the ideal gas, right? This is the ideal gas contained in this container volume V1, and what is the number of molecules of this ideal gas, and the mean free path, let's say at this particular temperature is lambda 1. Temperature is not going to change, rather they have changed the volume to V2, and the number has also changed of the molecules. They have changed the number of molecules also. So this is by half, and the mean free path, as they have told, this is actually uh, is 4 times of lambda 1. This is given here, 4 times of lambda 1 initial value. All right, so we know that the mean free path formula is kbt by under root kbt by under root 2 pi d square by p, where T is the temperature, K is the Boltzmann constant, P is the pressure inside on the wall of the container, and D is the diameter of the molecule. And P is given by 1 by 3 mn. This is the mn 1 by 3 mn bar V square, where bar V is the average velocity of the gas molecule, and is the number density of the gas molecule. M is the mass of each molecule. This formula is derived, if you remember, with the help of theory of kinetic gases. And if we substitute the value of P back into the formula of lambda, we are going to get this kind of expression, which tells you that for a single ideal gas at a particular temperature, lambda is actually inversely proportional to 1 over n, where n is the density of molecular density, because rest of the things are constant for a given gas at a given temperature. Right. So n is can be written as capital N by V. So lambda 1 by lambda 2 basically is V1 over V2 times N2 by N1. And lambda 2 is given as 4 lambda 1 in the question, and N2 was N1 by half. If I substitute those values, V1 by V2 is nothing, or turns out to be zero point 0.5. So zero point 0.5 is the answer. It was N80 type question, numerical answer type, and we had to answer like round off to one decimal place, which is essentially zero point 0.5. Okay, this was probably the last question of the from the thermodynamic section, that an ideal black body at temperature T emits radiation of energy density U. The corresponds the this corresponds value the corresponding value, the corresponding value for a material at temperature T by 2 is U by 256. Then we have to find out the emissivity of the material, right? So for a perfect black body, for an ideal black body, the emissivity is 1. So we write down the Stefan's law equal to sigma t to the power 4, u equal to sigma t to the power 4 according to the question. But for imperfect black body, or for a which is not the ideal black body, so this expression reads as E prime times sigma to the power 4. E prime is the emissivity, right? So, and here it's been said that at temperature T by 2, the energy density is U by 256. So if I substituted the value of E prime, that is for the imperfect black body, the same material at different temperature T by 2 doesn't work like an ideal black body. So in that case, I will have to keep this factor E prime over here. Sigma is of course the Stephen constant, and T to the power 4 is the temperature to the power 4 at T2 is nothing but T by 2. So if we write down E prime, which is nothing but U by 256 over in the left hand side, E prime, they have to calculate sigma, and as it is, and T2 is T2 T by 2 to the power 4, and U was nothing but sigma to the power 4. If I put in the left hand side, sigma cancels out, T to the power 4 cancels out, I get E prime as 1 over 16, which is nothing but 0.0625, which when approximated up to 3 decimal place turns out to be 0.063, because in the question it was asked that we have to round off our answer to 3 decimal places, and finally we got the answer as 0.063. So that's it for the thermodynamic portion. I will try to post the solution for other sections as well as soon as possible. Thank you so much. Well,